This is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. September 2023 was roughly 1.75 degrees warmer compared to the pre-industrial period. It was also 0.93 degrees C warmer than the 1991-2020 baseline, which is used as a practical tool for climate-sensitive sectors like agriculture, according to the World Meteorological Organization. Climate change is here. So what are we doing to meet the challenges in Europe? Ahead of the United Nations Climate Change Conference, COP23, we will be hearing from 4 cutting-edge researchers who are working to get us ready to deal with the coming changes to our environment. Tracking mosquitoes that carry diseases more often associated with the Global South, protecting our woodlands and forests from the impact of destructive beetles and other factors, examining the impact of extreme storms on our architecture, and working out how to keep people safe from waves that are higher than ever, overtopping coastal defences that were designed in another era. This episode is on adapting to climate change in Europe. Here to talk us through these ideas are our guests, whose work has been funded by the European Union. João Encarnação is the CEO of Irideon. He has an MSc in biochemical engineering and a PhD in sensors. He's particularly interested in the development of IoT, Internet of Things, sensors for insects with impact on public health, food, safety, and biodiversity. Welcome, João.
Hi, Abigail. Pleasure to be here.
Pleasure to have you. Guillaume Marie is an independent researcher mainly working in ecological modelling, with a strong focus in natural disturbance in interaction with human activities. He is an active developer of ORCHIDEE, the French land surface model used by the UN to predict climate change. Welcome, Guillaume.
Thank you very much.
Lovely to have you. Marie-Pierre Repetto is Professor of Structural Engineering at the University of Genova in Italy. Her main interest is in wind engineering, analysing the impact of wind on urban and natural environments. Welcome, Marie.
Hello, everybody. Thank you for inviting me.
You're welcome. Corrado Altomare is a postdoc researcher at the Maritime Engineering Laboratory of UPC in Barcelona and is actively involved in mounting Europe's response to the problem of wave overtopping. Corrado is particularly interested in studying the effect of sea waves on coastal structures and wave energy devices. Hi, Corrado.
Hi, Abigail. Hi, everybody. Very happy to be here.
And we're happy to have you. João. The VecTrack project wanted to find a new way of obtaining high-quality field information about the presence of mosquitoes that could be vectors of West Nile fever in Europe. Can you tell us what the impact of a warming planet is having on disease-carrying mosquitoes, please? West Nile fever isn't something normally that one would associate with the European Union. How is that affecting Europe now, and how might it affect it in the future?
Well, actually, the West Nile virus is becoming increasingly common in the European Union. Unfortunately, it's an arbovirus that is transmitted by the autochthonous mosquito in Europe, the Culex pipiens. And the issue is that besides the West Nile virus, there's a danger that Europe will start importing arboviruses that usually occur on the southern hemisphere of the planet, like dengue, yellow fever, Zika virus. And those are carried by invasive mosquitoes, like the Aedes albopictus mosquitoes, the famous tiger mosquito that came from Asia. And due to the increase of the temperature, the climate in Europe is becoming more and more suitable for those mosquitoes that come from the southern hemisphere. So it's a no-brainer. If the average temperature increases, we are creating the perfect conditions for mosquitoes to colonize the territory. And it's what is happening all over Europe.
Okay, you say it's happening already. I mean, it's not something that one, again, as I said before, it's not something that one necessarily associates with Europe. So are there cases of people catching these diseases from mosquitoes natively in Europe right now?
I can tell you a couple of some of the latest cases. We had reports of tourists getting dengue in Ibiza. There were also cases of dengue in France, if I'm not mistaken. And you have cases of malaria in Greece. The issue is that this is the kind of information that is available publicly if you consult the webpage of the European Centre for Disease Control, but it's something that the general public doesn't do, of course. So you may say that this is the kind of information that circulates among people that handle this kind of problem, public health technicians, or people like me that are interested in developing technology to help them solve this problem.
Right. So that makes your work and your project very, very timely. Can you tell us a little bit more about what Vectrac has developed to counter this threat?
The biggest challenge that you have when you have vectors that are capable of carrying diseases is that to stop the transmission, which is paramount to stop the outbreak, you have to monitor and control the vector. Let's look at the coronavirus. Humans are the vector. How did the World Health Organization and all the public health agencies in the world decided to stop the vector? Everybody locked down at their homes. You cannot do that with a mosquito. The mosquito roams freely out there, meaning that people are exposed to that vector. So that's quite a high-risk situation, because if you have an outbreak of a disease carried by a mosquito, as it happens normally in Southern Hemisphere countries, like, for instance, I don't know, the capital of Brazil, Brasilia, you get out to go to work, have a coffee, and you can be bitten and get dengue. Here in Europe, that's unthinkable. However, people there, they still live there and try to do their normal life. Here, the issue is that in the last 100 years, the technology to monitor mosquitoes hasn't changed a lot. So basically what entomologists do is that they deploy traps that capture mosquitoes, and with that they have an idea of the abundance and the type of mosquitoes that are being captured. Everything is done manually, everything. So the idea that we had was, what if traps could be smart enough to acquire the information automatically and send it to a computer? That way, entomologists would acquire the information automatically and basically in real time, and that would increase not only their time of response, but also save a lot of money in field work. And since the technology is aimed at saving time and acquiring data as fast as possible, that means that with that, we can improve a lot the way public health agencies or vector control technicians can fight the vector to prevent the outbreak of the disease. With current state of the art, and we actually time this, if you have an increase of a certain vector, let's say Culex pipiens, that can transmit the West Nile virus, for a standard public health agency with a standard lab where everything is collected manually, and then the samples are taken to lab, and they put the samples in a freezer, and then they have to find the time to inspect those samples. I can tell you that if today we had an explosion of Culex species anywhere in Barcelona, or in Lisbon, or in Berlin, or in Paris, whatever, the public health agency in charge of monitoring those vectors will probably know that it was happening 15 days later.
Wow.
With our technology, we know it when it's happening, while it's happening.
In real time.
In real time, yeah.
Now you need to this is fantastic information, because we have 15 days with the population increasing and exposure and all the rest of it. So this is a really remarkable difference in time frame. So now I need you to tell me a little bit more about actually what you've developed. So I know that it's optical thermosensors and so on, but please tell us more, because frankly, the idea of a sensor that can identify not just the species, but also the gender, you're only interested in the females, that's just blows my mind. So please tell me a little bit more about these sensors and how does it all come together?
The sensor is what we call an extinction sensor. Basically, what we measure is how much light is blocked by a mosquito when the mosquito crosses a field of near infrared light. With the sensor, we analyze not only the morphology of the insect, but we also track the kinetics, how the insect moves. That generates a spectrum that is like a fingerprint that has all the information about the insect. And then using machine learning techniques, we teach a model to interpret that data. And every time the model sees a specific mosquito, he will tell, oh, I've seen this one before. This is that.
That's fantastic.
The sensor can say, look, you have a fair amount of females of this species that is dangerous that were captured at trap number 59. You go there and take a sample immediately. And when you get the information that, we start having the circulation of disease, that can also be included in the model. So then, besides having models that tell you how mosquitoes are spreading, you can include information about viruses. And then you start having models that tell you what is the risk of viral circulation in the mosquito population and how that can impact on human population.
And that's fantastic.
This has never been done before, and this is actually ongoing work that is happening after the conclusion of VecTrack.
I know that you ran some pilot studies involving public health authorities to stress test and to prove the technology, and in fact, you had excellent results, didn't you?
Yes, indeed. We've conducted trials with public health entities in Spain, in Portugal, also in Brazil, and we have ongoing pilots happening in other countries. We've managed to prove that our technology can automatically differentiate these mosquitoes from other insects and can tell the species and the sex with average accuracies that are above 85%. Thanks to VecTrack, we have recently found out two very interesting things. We've recently found that we can determine the age of the mosquitoes and tell if they are young mosquitoes less than 5 days or more than 5 days, meaning that if they are females with less than 5 days, they are not a high-risk female to transmit diseases. But after 5 days, those females start getting more and more competent for infecting humans. And I have to also tell you that we've dabbled a bit with, can the sensor also tell the difference between a female infected with Zika virus or not?
Wow.
And that is also something that will be published soon.
That's amazing.
I was a bit skeptical, but the results were quite intriguing, let's say. Let's leave it at that.
Oh, okay. That's a teaser, isn't it? Well, that would
Yes,
just be
it's a teaser,
amazing.
yeah.
That would just be, given the spread of Zika, that would just be amazing. This is excellent work you're doing, João.
Thank you.
Does anyone have any questions for João? Yes, Guillaume.
João, the sensor you develop, do you think they can be adapted to bark beetles, flying insect, or in general in other flying insects?
If it's a flying insect, our tech will detect it. The secret is we develop the sensor, but then you have to have a trapping system that is designed for the particular species, because trapping insects is not a trivial thing. Incredibly, if it flies,
It can be identified.
we can develop a model to identify it automatically.
That would be particularly useful for the sandflies and leishmania.
That's one of the things that people are very interested in. We know that in mosquito traps, those kind of flies that transmit leishmania, they also fall in our trap, and we can see them in our data.
Mm.
That's basically, Abigail, those are episodes for the next season.
Yes. Yeah. Well, I could just talk with you all day. But listen, thank you very, very much for your time.
Thank you, Abigail.
You're very welcome. Guillaume, I'm going to turn to you now. The Climpro project asks whether a new generation of forest management is needed in the face of coming challenges. And one of these is the hugely destructive pest known as the bark beetle. So, Guillaume, you're also interested in how climate change will affect insect populations.
Thank you. Two things. First, it's like bark beetles are not in natural situation. They are not really destructive. They are part of the dynamics of the forest. So it's not something we can append to bark beetles. It's really something we can, the cause is really the human, and for two things. The first thing is that bark beetles, they like heat. And because of our impact on the temperature, bark beetles can increase the number of generations they can do in 1 year. The second point, it's more about the fact that forestry, they really plant like spruce, Norway spruce, in region where it was not naturally occur, especially in the lowland. So normally spruce is for a high mountain and very north Europe, but because of that, because of the two things, we put a fertile ground for the bark beetles, because now they can really proliferate and attacks a lot of forest in Europe.
So basically, we're creating the higher temperature that favors proliferation, as you say, and then we're also changing the habitat because we're bringing these trees into places that are not indigenous for them.
Yes, exactly.
Right, okay.
Just to give you some number, it's like if you have, let's say, 1 trees that are attacked by, let's say, 500 bark beetles, they will kill it. But these 500 bark beetles, they will produce 20,000 bark beetles. And after that, the spread can go very fast, especially if instead of 1 generation per year, you produce 3 generations like it occurs now in Europe.
And that's happening already?
Yeah, already. It's already there. In terms of ecology, the bark beetles is not a huge threat because, yes, some tree will die, but you will have a dynamic of regeneration and regrowth, and you will have a new forest, etc. The problem is economic because the wood, and especially the spruce wood, it's a very valuable wood market. And when this bark beetle outbreak happen, you suddenly have a lot of wood available on the market because they have to cut it, they have to sell it, and also because you have to store and stock this wood. And all these things, they cost a lot for the manager. And here we are talking about an economic disaster, not a natural disaster. It's something very different, and I want to highlight that.
Yeah, no, indeed. I mean, it's an important difference, absolutely. So what did your project try to do to counter this? What was Climpro's approach here?
So Climpro, it's really, I would say, a modeling project, because what we're trying to do, it's include this kind of disturbances when we account for carbon balance at large scale. So we are using a model, a land surface model called ORCHIDEE. So it's a model that simulates the surface of the planet. So it's really meant to be large scale. And this kind of model, they are coupled with what we call general circulation models. And with that, we can predict what would be the future climate. So it's really a big piece of this kind of prediction. We need to know if disturbances, drastic disturbances, they have an impact on this kind of release. Because before that, I would say the classic way of including mortality, tree mortality, is by taking fixed mortality rate. Let's say 1% per year. So every year we remove 1%. As you can understand, it's very smooth. So there is no abrupt event. And what we want to see, it's when we remove this background, this 1%, and replace it by abrupt event of 20, 30% mortality, what would happen in the function of this ecosystem? And if this drastic event will affect the release of CO2 in the atmosphere.
And when you ran these simulations, what did you find? And how do you hope this information can be used?
When we run simulation, we start thinking, okay, we will see some effect on everything, but the first things we see, it's like bark beetle, they thin the forest and they act as a manager at the end. It was really interesting to see that. So without any referring to economy, you just see like bark beetles acting as manager. But when we look at the global net carbon emission over a large period of time, we see that not including disturbances can really underestimate the net flux of CO2 into the atmosphere. So we are really convinced right now that we need to include it.
Yeah, sure. So what you're saying is that if you don't actually track what's happening to the forests accurately with regards to the possibility of a large-scale sudden impact, you can't assess how much carbon dioxide is going to be trapped by the forests.
Yeah.
You're saying released by the forests. That's confusing me slightly.
No, really, sorry. Yeah, because we trapped, but what we are interested in it's the net release. So
yes,
what they keep minus what they release.
Okay, that's fascinating. Thank you very much indeed. That's excellent. I'm just going to turn now actually to Marie. Thunder set out to create a model for thunderstorm outflows and the impact that they have on the urban environment. I've never really thought about the impact of wind on buildings, Marie. Can you explain why we should be bearing it in mind, actually?
Yes, wind is one of the most dangerous and costly natural hazards. Wind loading is always considered as a main action in the design of buildings. But what is new now is the impact of thunderstorm winds, which is particularly intense and destructive. Moreover, many studies indicate that the intensity and the frequency of this kind of events may grow due to the climate change. Thunderstorms are meteorological phenomena that are generated in a small area and evolve in a few minutes. And during those events, a bulk of cold air falls down, impinging the ground and spreading radially. And this is called downburst because it's something similar to an explosion of air. And it generates a large vortex with a strong velocity and a large energy also. So if this downburst hits a building, it can cause serious damages and also dangerous situation.
So, Maria, what have people been doing up until now?
Thunderstorms are present from ever and ever, but now they are increasing in their intensity and in frequency. And we are seeing many, many more damages in buildings, typically low-rise buildings or flexible buildings, poles, and also bridges.
So what were you actually doing with your project? You wanted, I think, to improve the ability to plan for architects, no?
The aim of our project is to bring together experts from different sectors like meteorology, like engineering or atmospheric physics, to study together the problem and to produce models that can be used from architects and engineers.
And how did you go about producing these models? What sort of tools and techniques did you use?
So, air is something invisible, and while waves and vortices can be seen and observed in water and sea, the same phenomena can happen in the air but cannot be seen. So, our first aim was to improve the capability to detect the downburst and the thunderstorm development. So we managed to use a variety of sensors to detect the wind strength, direction, and to catch how the downburst move. We installed a very sophisticated LiDAR, which is able to measure the way the outflow of the thunderstorm develops and change during the storms itself.
I'm just going to stop you for a second. So LiDAR is a mechanism by which you can look at the surface of a certain structure and see the impact of what's happening on the surface. Is that correct?
Yes, this is one of the possible use of LiDAR. In the air, we use it to measure the movement of the particles, so we can reproduce in some way the wind flow.
So basically, you're almost making it visible. You know, you were just saying that you could see it in water.
Yes.
So it's a way of making air and the vortexes and the downblasts visible, so you can actually see what's happening with the thunderstorm. Is that right?
Yes.
Right.
This is exactly the idea, to see the phenomena, to see the vortex, and to see how they move inside the air. The second part was to reproduce this kind of phenomenon by means of experiment in a very special wind tunnel in Canada, and also to reproduce it numerically.
This actually sounds like a lot of fun.
Yes.
I think this does sound like it sounds really fun. Yeah.
Yes, and also in this case, we tried to visualize the wind flow in the wind tunnel, and we have a beautiful picture of this primary vortex, is called, that hit the laboratory people also.
Okay.
And also, finally, we detected the impact on structure, and we tried to develop a model. And in this case, we were inspired by a method adopted in the earthquake or blast effects, because in some way, the evolution of the thunderstorm action is something similar, very rapid and very energetic, but short in time.
Yeah.
So.
Okay. Thank you very much. I think that's absolutely fascinating. Corrado, your project considered the fact that low-lying coastal areas are very vulnerable to rising sea levels, as we appreciate, and the towering waves produced by storms as they get perhaps potentially more aggressive, if one can use that word. Dirkwave wanted to develop models to reflect the situation as it is now, and that will evolve to help people estimate the vulnerability of coastal zones to climate change. Corrado, what inspired you to get involved with this area of research?
Well, Abigail, I'm from a coastal town from the Adriatic Sea. So, I lived along the sea, and I was always fascinated by all these kind of processes. I'm still the one that is running to the coast or and a harbor to see where there is a storm, what is happening there. So yeah, this phenomena that we call like overtopping is where when the water passes over the structure, and can generate flooding and can generate a lot of problems and damages, and also can represent a risk scenarios for people, for pedestrians, for people living there. So yeah, just imagine that 40% of the population in the world live along the coastline. Now, making a number in Europe, this means 80 million people, and the trend is increasing. And beside that, we have climate change, sea level rise. As Maria said also, more storms, more unpredictable sometimes storms. So all this combination makes that we have to look more in deep to what is this kind of wave overtopping that is very common, but at the same time, very diverse and very different from site to site.
Yeah, that's fascinating, isn't it? Because, I mean, it sounds relatively simple. Wave overtopping, very, very large wave, out of control, coming into land and overtopping something. But of course, it must be entirely context dependent. I mean, it's not only the context of the particular storm and the particular wind direction, but also the infrastructure and so on and so on. So it must be difficult to model something that has so many different types of criteria. Could you tell me a little bit more about that process? What did DERCOWAVE want to do? You've explained why a little bit, but perhaps you could tell me how a little bit.
Yeah, well, DERCOWAVE wanted to contribute, let's say, to enhance the design of coastal defenses, but especially, as you mentioned in the introduction, those coastal defenses in urbanized coastal areas. So to do that, DERCOWAVE pretended to combine different tools. So from one side, we have, again, modeling, experimental modeling, lab tests, okay, in a wave flume. Usually I say, if I have to explain to my 4-year-old daughter what I do for work, I say, I play doing waves. And it's true. We do waves in a flume, and we measure certain results. And then we do numerically. So we do with some solver that, in particular in DERCOWAVE, was a particle-based solver. And
what does that mean? Sorry, Corrado, I'm stepping in here. What do you mean particle-based solver? What is this?
Well, we have two kind of, let's say, approaches. A more traditional one where you discretize an element that can be your fluid, your water, let's say, in a set of points, and then you calculate what is happening there. Like you're measuring in one point in space what is happening, just to explain simply. And then you have this kind of, they are called Lagrangian approaches, where actually your water is made of a sort of a set of particles that are free to move. It's very, let's say, from an intuitive point of view, it's very easy to understand if you look at some video or some animation or some simulation of it. So in that sense, among all this kind of method and model, I have used a particular one, a particular model that is called dualist physics, which has been used to reproduce wave overtopping for specific coastal layouts.
Okay, I get it. So basically using just like a point concept is a little bit too reductive and a little bit too simplistic. And what you actually want to do is simulate the movement of a body of water.
Correct.
And that body of water is made up of a multiplicity of particles. And so you look at the whole thing and how it moves together, rather than just, for example, plotting peaks and troughs and so on.
And the point of having this kind of points of particles that are moving, it means that it's inherently easy to model very, let's say, violent phenomena.
Is this the whole time that a storm in the project DERCOWAVE, is that the whole time that a storm was simulated from start to finish?
In a particles-based method, as I mentioned before, yes. Actually, what I did was to simulate an whole storm. And when I say a whole storm, it means like a storm lasting 1,000 waves. Imagine 3 hours in reality, something like that. So that was the first time. Yes.
And what sort of things are your simulations showing us? What are you learning? What do we need to know?
Yeah, all we have done experimentally and numerically was meant to gain further insight into what we call overtopping flow properties. That, in a nutshell, means the velocities of these flows, and let's say the quantity of water, or if you like, the height of this flow where is flooding. Why that? Because the combination of velocity and flow height or flow depth, if you like, is very important for the safety of the people, for people's stability. You can feel a flow where it is where you are your feet into it, whether it's faster, whether it's bigger, etc., etc. So can cause casualties, but also can be related to security of infrastructure and your amenities along the coastline, etc., etc.
Okay, and are you starting to see that architects and planners are taking into consideration the kind of models that you're producing? Or is there interest in that kind of sector?
Well, I'm happy to say yes. You know, when I was carrying out the project, just a big storm hit the southern coast of France and the Mediterranean coast of Spain. We have several damages. And some local authorities started to implement the outcomes, but also the method of the Archwave project in some harbor to study what happened actually during this storm that was called Gloria, or like a pier structure just north of Barcelona here in Spain, where I am. So I have seen that little by little, this kind of method and outcomes are becoming more and more popular and used by local authorities.
Yeah, and planners maybe. Okay, super. Thank you very much, Corrado. And I must just mention that I love your surname in connection to your work because it means high seas.
Yeah.
How appropriate is that? Well, thank you very much indeed for spending time with me today to discuss your important work. And it is indeed important given the fact that we are, in all probability, due for more of these changes in the near future. So thanks for spending your time with me today.
Thanks, Abigail. Thanks.
Thank you.
Thank you.
Cheers. Thank you so much.
Goodbye.
Goodbye.
Bye.
Bye.
Bye-bye.
If you've enjoyed this podcast and are interested in the latest scientific research coming out of the EU, have a listen to previous episodes. Follow us on Spotify and Apple Podcasts and check out the podcast homepage on the Cordis website. We've considered how chemicals produced in our gut can impact on our brain cells and how plant roots communicate with the bacteria around them. In our last 30 episodes, there'll be something there to tweak your curiosity. Perhaps you're interested in knowing how other EU-funded projects are working to help us adapt to climate change. The Cordis website will give you an insight into the results of projects funded by Horizon 2020 and Horizon Europe that are working in this area. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from photons to neurons. There's something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line, editorial@cordis.europa.eu. Until next time.